Hey, so let's start off with some sample diploma questions. So this one is a tricky one. So how much work is required to move an electron from location 1 to location 2? So I got new pen. Oops. There we go. Okay, so it's working. So if we have so this is the ground, right? If I move it from here to here, compared to from here to here, and we're talking about potential energy, so EP is equal to mgh, right? Is there a different amount of gravitational potential energy? And the answer is no, there's not, because we go by our vertical height, right? So it's the same thing for electrical potential energy, right? We go by our height. So we don't actually want to find a hypotenuse side like this. We just want to use, so if we go from here to here, that's going to be the same as 1 to 2. It doesn't make a difference. Okay. So the easiest way to do this question, there's a few different ways, is work equals force times distance, right? And it's force electric. So if we want to find work, force electric equals electric field times Q times distance, and then electric field equals voltage over distance times Q times D. So you would think that, oh, there's a D on top, D on the bottom, that's going to cancel out, but it's not, right? So if we look at this right here, this is voltage over distance. So we know the voltage across both plates here, right? So this voltage only works if we're going across 0.20 meters, right? That's where that distance comes from. But force times distance, this is the distance we actually move it, so that's going to be the 0.16. So in doing this question, I'm just going to move up top here. So our voltage is 1.2 times 10 to the 3. I'm still getting used to this pen. Sorry, let me try again. 1.2 times 10 to the 3 volts, and the distance across the whole plate is 0.2 meters, right? So we're going to multiply that by our charge. So it's talking about an electron, so that'd be the charge of an electron, 1.6 times 10 to the negative 19 coulombs, right? And we want to multiply that by our distance across the plates, which is 0.16 meters, because that's how much we actually move it. So if we plug all of that into our calculator, just let me start up the calculator here. So if we go 1.2 times 10 to the 3, so everything on top, because it's all multiplied, so it doesn't matter, times 1.6 times 10 to the negative 19 times 0.16 divided by 0.2. Then you end up getting 1.536 times 10 to the negative 16, which makes B the correct answer. Okay, that's how you do that one. This one here, pair of parallel plates is separated by a distance of 1 centimeter and is connected to a 12-volt battery. The magnitude of the electric field between the plates is E1. Okay, so this is a second pair of parallel plates first. So we can just do a calculation here, right? So E1 is equal to voltage over distance. So that's going to be 12 over 1. It shouldn't be in centimeters, but it doesn't matter because we're not actually getting answers. So that's going to be 12. And then E2 is equal to voltage over distance. So E2 would be 6 volts divided by 3 centimeters, which would equal 2. So it looks like E1 is 6 times 2, which that's what A says. Oh wait, no, that's not right. 2 times 12 wouldn't equal 2. We want E1 is 12. 12 times 1 over 6. Yeah, that's what we want. We want D is the correct answer. Ooh, that's tricky. That's real tricky. Okay, question 4. An electron accelerates in an electric field and moves further from the negatively charged plate, the kinetic energy blank. Because the potential energy blank, the work is done by the electric blank. So an electron accelerates in an electric field and moves further from the negatively charged plate. So we have a negative plate. Oh man, it's still doing that thing. We have a positive plate. So the electron is moving this way, right? So here it has lots of EPE, and then here it's switching into EK. So that means that our kinetic energy is increasing, and then our potential energy is decreasing, and then the work done. So if we look at the work formula, work is equal to force times distance. So work is done by a force, not a field. So B is the correct answer. An electron is initially at rest at a negatively charged plate. At the instant illustrated below, the electron has 50 electron volts of kinetic energy. At any point along the path, the sum of the kinetic energy of the electron and its electric potential energy will be, okay, this one's tricky as well. So at the instant illustrated below, this has 50 electron volts of kinetic energy. So an electron is initially at rest at the negatively charged plate. So it's at rest here, right? Cool. So as our electron go through 215 volts, it'll get 215 electron volts of energy, right? That's the total amount of energy that it has available. So here, my EPE is equal to 215 electron volts. Here, my EK is 215 electron volts. And then here, if it's 50, is my EK, 50 electron volts, then it's just going to be, what, 185, 175? 165. So 165 of EPE is going to be right here, and the rest is EK. But it's asking for the total amount, so the total amount is going to be 215 electron volts. So this one we've seen before, but this is more of a calculation style question. So the magnitude of the charge on the sphere. So we dangle it like that. Okay, I'm going to switch to my whiteboard for this one because it's a little bit easier. So let's start this off by drawing a free body diagram. So we've drawn this one before, right? We have our force of tension up here. It tells us that it's 8 degrees from the horizontal. We have our FG here, and we have our force electric here. So then from this, because it's stationary, we can draw a tip to tail. This is 8 degrees right here. And we can solve this because we know the mass of it, right? So we know the angle, we know this side, this is opposite, this is adjacent. So you set it up with tan theta equals opposite over adjacent. Move the adjacent up here because we want to find opposite. So this adjacent here is FG. So I can just go mg tan theta over opposite just like we did on our lab. And this will find my FE, right? Yeah, I guess I can just keep going. It doesn't matter. So I know that this is equal to FE. We also know that FE is equal to EQ, right? I can break this down into that. And this is what we're looking for in this question. So if I move my electric field down below. I can do it all in one. Right? So I'll move it over here. So my mass in the question is 3.5, yes, that's on the screen, times 10 to the negative 2 kilograms, or 10 to the negative 4 kilograms, times 9.81 meters per second squared. Right? That's mg, tan of 8 degrees, all divided by electric field, which they also give us in this question, 6.57 times 10 to the 3 volts per meter. And then I'm ready to type that all into my calculator. 3.5 times 10 to the negative 4 times 9.81 times tan of 8 degrees divided by 6.57 times 10 to the 3. Nothing squared or anything like that. And we get 7.3 times 10 to the 8, which is this guy right here. So D is the correct answer. Okay, so we got a projectile motion question. Cool. So starting projectile motion questions, what you want to do is, I'm just going to switch to my other screen again. So we want to do a free body diagram. So it's a beam of electrons, right? Your electrons go like this. So obviously it's attracted to this plate. So that's positive, that's negative. When it's in the middle here, it experiences an electric force up. We don't need gravity because it's a subatomic particle and its mass is so small. So its gravity, force of gravity is negligible. So we can write our F net is equal to Fe, Ma is equal to Eq, and we can figure out acceleration from that, basically. That's what we'll end up doing. And what we also need is X and Y. So there's no forces on the X, so that's physics principle 0, physics principle 1, V, D, T, VI, VF, DAT. And let's fill in what we know. Right, so we know the initial speed, 9 times 10 to the 6. I don't have room for units in there. We know that in the X, no, we don't know. We're trying to find in the X, we're trying to find this. So we need time. So in the Y, its initial velocity is 0. The distance it moves in the Y is 2 centimeters. And then we'll need the acceleration from this. So I'm going to go down here. The electric field given in the question, 3.1 times 10 to the 3. It's an electron, so 1.6 times 10 to the negative 19 coulombs. And then the mass is 9.11 times 10 to the negative 31 kilograms. So that'll give us our acceleration. Okay, so that's our acceleration, 5.44 times 10 to the 14. Okay, so we need time. So we're going to use D equals VIT plus 1/2 AT squared. Initial velocity is 0, so we move our 2 up top, our A down below, and our square root down there. So 2 times our distance in our Y divided by our acceleration, and then we square root it. So let's plug that into the calculator. 2 times 0.02 divided by our acceleration, and we square root our answer, and we get a super tiny time, which makes sense, of 8.57 times 10 to the negative 9. Right, and then we finish it off with v equals d over t. So v equals d over t. So I'm going to multiply my velocity, this, times my time. So I just need to take my time from my calculator and multiply it by 9 times 10 to the 6. And it's about 7.7 centimeters. And that's what it wants the answer in, is this. Ooh, it wants 3 digits. So 3 digits would be 7.71. Okay, and that's what I'm going to put as my answer. I'm going to put, 7.71. Okay, that's how you do that one. What physics principle did we use? Well, I showed you what physics principles we used. So we used, in the X, we used physics principle 0. This one we used 1. It says you used first, use second. It doesn't matter which one you put first and second. It'll 1, 0, 0, 1. It marks them both correct. So this lesson is Millikan's oil drop experiment, and it's talking about how do we find the smallest possible charge, which is our first talking of the word quantum. Ooh, scary word. So explain Millikan's oil drop experiments and its significance to relative and charge quantization, new word. Analyze with numbers the motion of electric charge following a stated curved path in a uniform field using Newton's second law of vector addition and conservation of energy. Use a free body diagram to describe forces acting on a charge in a field. And that's all. So instead of explaining Millikan's oil drop experiment, I'm going to show you this video of Millikan's oil drop experiment. And yeah, it explains everything really nicely.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
So to summarize, what he did was he had a fine mist of oil droplets which sprayed into an atomizer between charge plates. So what an atomizer does is it gives them positive or negative charges. We talked about shooting X-rays at it, it gives them positive or negative charges. So by varying the voltage, Millikan was able to suspend or accelerate some of those oil droplets. The oil droplet radii were measured through a microscope, and he could get a volume. He knew the density of the oil, so he could figure out the exact weight of them. We would never have to do that or anything like that. That's not in the curriculum. Okay. So that was his experiment. Okay. So yeah. So let's do a board question. So let's draw some free body diagrams for these different scenarios. So pause the video and try them out. So if it was suspended between plates, what would that look like? So force of gravity is always down. And then force of electric is up. And if they're suspended, they're going to be the same size. Okay. So accelerating up at 4 meters per second, right? Our force of gravity is always down. And if we're accelerating up, then we need a net force up. So our electric force is up. Moving at a constant velocity. Same as the first one, right? Our force of gravity and our force electric are the same. So those are the same. Right? No net force, no acceleration, constant velocities, exact same free body diagram is suspended between the plates. And then this one here, accelerating down at 5 meters per second. So our gravity is down, and our electric is up, but our force of gravity is bigger than our electric. Okay, and then we got one more. Accelerating down at 15 meters per second squared. So if we think about this one, so say I just had a force of gravity downwards. What would my acceleration be? 9.81, right? So gravity alone can't make it travel faster than 9.81. So the only way for this to work is if there was another force helping accelerate it. So the force electric would be like that, and then we'd have to switch all of these to positives and these to negatives over here, and then that would work. But we'd have to switch our plates to make that work. So if it's accelerating faster than 9.81, it needs those two forces working in the same direction. Trick one. So Millikan did this experiment. He got all these numbers, and how did he find the elementary charge from that? Right. So this was all the different numbers that he found, and we'll do. Maybe I want to go back here to this picture. The suspended was the most useful one, right? Because if Fe is equal to Fg, then you can break this down into EQ and break this down into mg. And if we want to find our charge, just move our electric field down there. And you can measure the electric field. He knew the mass, he knew g, so he found the charge with that. So that's what he did to find that charge. So with those numbers of charge, you got all different ones, right? So you got this one here, you got this one here, you got all these different charges. Well, what does that mean? Okay. Well, what he did is he found the smallest charge. So this was the smallest possible charge, right? We want the smallest this number, while the biggest to the negative, right? And if you look all around, there's nothing to the 19 other than this, and 3.2 is bigger than 1.6. So then what he did was he took all his numbers, divided it by that smallest possible charge, and then he ended up getting these nice whole numbers. So what does that mean? Well, it means that this, if it has a negative charge, is 1 extra electron. This one has 2 extra electrons. This one has 3 extra electrons. And what that also means is that electrons are quantum. What does that mean? Well, quantum means they're the smallest possible thing. So if you think about it, so if you take a piece of paper, you rip it in half, you rip it in half again, you rip it in half again, you rip it smaller and smaller and smaller, eventually you should reach the smallest thing, right? What is that going to be? You rip it apart. Paper is mostly carbon. You rip the carbon apart. Okay, it's got protons, neutrons, electrons. You rip that apart. Well, is there anything smaller than that? That's the same idea, right? So 1 electron seems to be the smallest charge, right? If I have 2 electrons, I have a bigger charge. 3 electrons, I have a bigger charge. But the fact that this is the smallest possible thing means that the electron is quantum. There's the smallest possible thing. That's what quantum means. You can have 1, you can have 2, you can have 3, but you can't have 2.5. That's the idea behind quantum, right? It's like a staircase. You can be on step 1, step 2, but you'd never be on step 2.5. That doesn't make any sense. So that's what he found, is that electrons' charge is quantum, 1, 2, or 3. So let's do an example. So a 2.5 times 10 to the 13 kilogram oil drop accelerates upwards at a rate of 2.8 meters per second squared when placed between two horizontal parallel plates. They give us a distance, a voltage. Let's draw a free body diagram, determine the magnitude of the charge on the oil drop, and determine the number of excess electrons. Okay, let's do that. So I'm going to switch to my whiteboard screen, erase all this. So we have plates. And we have an oil droplet. And it accelerates upwards. So that means that we have force of gravity. So there's a bigger force electric in between there. And that's all it really tells us. Okay, just wanted to make sure that's all it really tells us. So we can write an F net equation. So F net, I'm going to make this positive, this negative, is Fe minus Fg. Right, we want to find the magnitude of the charge, which is going to be in here. So I'm going to add an Fg to both sides. So we get F net plus Fg is equal to Fe. Okay, mass times acceleration, mg, and then this is going to be EQ. So I'll move my electric field down below like that, and that's how we'd find the charge. We've done questions. This is just an elevator question. We did these in Physics 20. They don't actually give me electric field. They give me a voltage and a distance. So I'm going to throw a voltage distance down there like that. I don't normally like to do that, but I can put this in brackets, move distance to the top, but I think it's fine. Okay, so the mass of my oil drop is 2.5 times 10 to the negative 13 kilograms. And my acceleration is 2.8 meters per second squared. And then we're going to add that to 2.5 times 10 to the negative 13 kilograms times my G 9.81. And we're going to divide it by my voltage, 890 over 0.34 meters. Okay. Yeah, so we're ready to plug that into our calculator. .5 times 10 to the negative 13 times 2.8, close my bracket, 2.5 times 10 to the negative 13 times 9.81. I'll find an answer for the top, and then on the bottom, I'll divide it by 890 over 0.34. Let's put that in brackets. And you end up getting this is our charge 1.2 times 10 to the negative 15 coulombs. Okay, I was just trying to look. It doesn't really say if it's positive or negative with this one, because you could have, if this was a positive charge, then this would be negative, but if it's negative, this would be positive. But it does say determine the number of excess electrons, so we have to assume that this has a negative charge because it's excess electrons. Okay, so I'm going to assume this is negative. This is my positive plate over here. Negative plate, but yeah, not the greatest. So to determine the number of excess electrons, what we do is we have 1.2 times 10 to the negative 15 coulombs, and we know that 1 electron is equal to 1.6 times 10 to the negative 19 coulombs. So coulombs cancel out with coulombs. That's why I put coulombs on the bottom. So we divide it by the elementary charge. So I take this, divide it by 1.6 times 10 to the negative 19. Right? And we get this. So in terms of sig digs, because electrons are quantum, you can have 1, you can have 2, but you can't have 0.03. Because of rounding, we're never going to get the perfect answer, but the best answer for this is 7527 electrons, right? Don't ever do a decimal when finding the number of excess electrons because you can't have less than one. It's the smallest possible charge, it's quantum. So we have a couple more questions that we're going to do. So we have this one here. So we have another oil droplet having a charge and magnitude. So this one tells us it's negative. It's good. It enters electric field between plates that are 8 centimeters apart. The drop passes through undeflected. So that's a really key thing right there. If it passes through undeflected, that means that we're going to have equal forces. Okay, nice uniform speed. Excellent. So let's draw all of this. So let's do it on the whiteboard here. So we have plates. It's a negative charge passing through, and it passes through undeflected. The only way it can pass through undeflected is if my electric and my gravity are equal to each other. If it's force electric up, then it's going to be like that. So that's our free body diagram. It wants to draw our field lines. Our field lines are the direction Pedro would go. So it would be downwards. And we want to determine the potential difference between the plates. Fe is equal to Fg. EQ is equal to mg. This one we can break down into voltage over distance. Voltage over distance is this. And we're trying to find the voltage between the plates. Move distance up there, Q down below, and we're ready to go. Okay, so our mass is 5.8 times 10 to the negative 9 kilograms times 9.81 times our distance between the plates, 0.08 meters. And our charge is 5.4 times 10 to the negative 14 coulombs. And that'll give us our charge, that'll give us our voltage. 5.8 times 10 to the negative 9 times 9.81 times 0.08 divided by 5.4 times 10 to the negative 14, and we get, this big one, 85 kilovolts. 85 times 10 to the 3 volts, 84. Ooh, rounding error. Do we only have 2 sig digs? No, we have 3 sig digs. So this is terrible. 84.3 kilovolts is the answer. 84.3 to the right number of sig digs. Sorry about that. Okay, we got one more question. So those are the two, right? Either they're balanced or one is bigger than the other. Not too tough. We got one more question. So we're going to do this one. So this is a projectile motion question, but with our oil drop type thing. Okay, so it's important to know the difference between the questions we did before and these Millikan oil drop questions. These Millikan oil drops have a significant mass here, right? This is a pretty big mass compared to an electron, which has a mass of 9.11 times 10 to the negative 31 kilograms, right? This is our electron. This is our subatomic particle. This here is an oil drop. So this has Fg. This does not have Fg. And that's how you sort of know the difference between the questions. So this, we include force of gravity in our free body diagram. Okay, so let's do that. Let's draw a free body diagram. Let's figure out what's happening. And it's just a projectile motion with an extra force. Okay. So we have our plates. It's going like this, like that. So when it's between these plates, because it has a big mass, obviously it feels electric up, but our force of gravity is downwards like that. So when we write an F net equation, it's going to be positive force electric, negative force of gravity. So it's a little bit more work, right? We're trying to find the potential difference between the plates, which is in here. So I'm going to add of Fg to both sides, and we get F net plus Fg is equal to Fe, and we can break all these down. This is Ma, this is Mg, this is Eq, and then we're trying to find this. Well, actually, let me break down Eq into voltage over distance. Right, so I'll move this distance up top and this Q down below. So what do we know, what do we don't know? So we know distance, we know our charge, yep. We know our masses, we know our G, but we don't know our acceleration. So we still don't know that. So what we have to do, where you go next, so we have X, we have Y, and the X it's going at constant speed. In the Y, it's accelerating. We want to find out what this acceleration is. So initially, it's just moving the X at 5 meters per second. Initially, in the Y, it's 0. It moves a distance upwards of 0.2 meters. Right? And then the X, it moves a distance of 1.5 meters. So we have enough information for time. V equals d over t. T equals d over v. So if we plug that in, so we want distance over velocity, so 1.5 divided by 5, and we get 0.3. So that's our time, 0.3 seconds, 0.3 seconds, and then we can use d equals VIT plus 1/2 AT squared, and we can find our acceleration, move the 2 up top, move the 2 squared, t squared down below. So 2 times 0.2 meters divided by 0.3 squared, and that'll give us our acceleration. So let's find our acceleration. So 2 times 0.2 divided by 0.3 squared. And we get our acceleration to be 4.4 repeated. Okay, so now we are ready to plug stuff into this equation here. So I'm just going to erase what we just found, the 4.4 repeated, so I have room. Okay, let's do the stuff in the brackets first. So my mass is 1.2 times 10 to the negative 6 kilograms. My acceleration is at 4.4 repeated. Make sure to use the repeated. 1.2 times 10 to the negative 6 kilograms times 9.81. Okay, so find an answer for this first. Our charge is 0.5 microcoulombs. And this distance here, this is tricky, right? So this distance came from here. And when we talk about voltage over distance, we have to be careful. What distance is this? Well, this is the distance across our whole plates. We want the voltage across the whole plates, so we want the distance across the whole plates, which is 0.3. So 0.3 meters, which is different than this distance here. We just wanted the distance that it moved. Ooh, really tricky there. Okay, so let's plug that all into our calculator. So I'll do the stuff in the brackets first. 1.2 e negative 6 times 4.4 repeated. Oops, got rid of my answer, so I'll just do a whole bunch of 4s. 1.2 times 10 to the negative 6 times 9.81. And I get an answer for that, so I'll multiply it by 0.3 divided by 0.5 times 10 to the negative 6. And that's it. I don't need to do anything else to it. So our voltage across the plates looks like it is 10.3 volts. And we're done. That is all. Okay, so these are your different style of questions. It looks like a lot, but there's only a couple of each style, so we'll give them a go. And yeah, we are, because this is last before the quiz, we are going to do this sample diploma question, so give it a go on your own. So an oil drop is suspended. So suspended oil drop is Fg and Fe, where our Fe is equal to our Fg, and we want to find excess electrons, so we want to know the charge first. So E over EQ is equal to mg, so I'll move my electric field down below, and we can figure it out. So my mass, 6.6 times 10 to the negative 14 kilograms. G is 9.81 meters per second squared. And then my electric field, 2 times 10 to the 6 newtons per coulomb. So let's calculate that. 6.6 times 10 to the negative 14 times 9.81 divided by, can't read my own writing, 2 times 10 to the 6. Right, so that's our charge. If we divide it by the elementary charge, 1.6 times 10 to the negative 19, it'll tell us how many excess electrons are in there, so there's 2. So it looks like B is the answer. And that's it.